Math 2, Semester 2, Power Standard 7 Review. Number 1, completely factor. Anytime you're factoring, you want to divide out a greatest common factor if one exists. So when I look at those two terms, both terms are divisible by a 4, and they do not share any variables in common. So I divide out the 4, and then for the leftovers, 8 divided by 4 is 2, and the xy drag down. Negative 12 divided by 4 is negative 3, and the w drags down. If you were to multiply your answer back out, you would get what you started with. Number 2, still factoring. So when I look at those terms, both of the terms have at least an x squared, and that is the only thing they have in common. So I'm going to divide out a greatest common factor of x squared. So for that first term, when you're dividing like bases, you have to subtract the exponents. So 5 minus 2 is 3. For the second term, the 8 drags down, x squared divided by itself cancels out, and then drag down the m. For number 3, all of those terms are divisible by a 3, and all of those terms have at least an x. So we need to divide out a greatest common factor of 3x. As far as the leftovers go, remember x is the same as x to the invisible 1. So when we're dividing like bases, we need to subtract the exponents. So the 3 divided by 3 cancels out. X to the 4th divided by x to the 1st is x to the 3rd. And then 6 divided by 3 is 2. X to the 3rd divided by x to the 1st would be x squared, because 3 minus 1 is 2. And then in the back, negative 9 divided by 3 is negative 3. And x divided by itself cancels out. Number 4, graph the following. X is greater than or equal to 5. So I'm going to draw a little number line for all of these. And then remember, when you have the little half equal sign in your symbol, it means you want a closed circle. And when you don't have the little half equal sign, it means you want an open circle. So x is greater than or equal to 5. Put a 5, put a closed circle, so shade it in. And then if it's greater than, so you have to shade to the right. And then for number 5, x is less than 9. So you want an open circle, and then you're shading to the left because it's less than. On 6, you have a 5 and an 8. And x is less than 5, and there's no little half equal sign, so you want an open circle. And then x is greater than or equal to 8, so there is the little half equal sign. So closed circle at 8, and then shade to the right. Number 7, we have a negative 4 and a 2. X is less than 2, so no little half equal sign, so open circle, and then shading left. And then x is greater than negative 4, so open circle and shading to the right. Since this is an and problem, our final answer is the overlap of our two graphs. So our final answer would be, let me change colors here, would be right here, this in-between part. So it's only the overlap of the two lines. Number 8, a village is designing a rectangular ice skating rink with square hot cocoa huts on both sides. They can make the rink and huts as wide as they want, but they can't exceed 200 feet in total length. Let W represent the width of each square section. So W is the width of the square section. So basically all of these would be W's along the edge here. And then the 200 is all the way across. So if I want just this shaded part right here that I'm highlighting in blue, it would be the 200 minus the 2W. So when it says to do an expression for length, that's the 200 minus 2W that we just saw visually in the blue part in the picture. And then the expression for width is just the W from before. On part B, write the function for the area of the rink, A of W, in terms of the width W. So an area of a rectangle is just length times width, or base times height. So W times 200 minus 2W. Number 9, Given the basic function f of x equals absolute value of x, use coordinate notation to describe how each point xy on the graph f of x becomes a point on the graph of the transformed function. So the 1/3 in the front is a vertical compression, so it's going to affect the y coordinate. So I'm going to take whatever my y coordinate is, and I'm going to multiply it by 1/3. Then the +2 in the back is a vertical translation, so that's going to take my y value and move it up 2. Then the +5 inside the parentheses makes me move left 5. So if I'm going to move left 5, I want to take my x values and I want to make them smaller. So I actually want to subtract 5 from my x coordinate. So everything's kind of as it should be, except those vertical ones are always the opposite. So vertical compression. On 10, given f of x equals absolute value of x, describe the transformations performed on the graph of f of x to get g of x equals f of x plus 7 plus 9. So inside the parentheses, it's always the opposite of what we think it should be. So that would be our horizontal translation, left 7. So horizontal translation, left 7. And then in the back, the plus 9, that would be our vertical translation, and they're as they should be. So up is positive, down is negative. So vertical translation, up 9. On 11, they want us to graph that function. So your normal absolute value function starts at the origin. That's where the point of the v is. So we're going to take the point of the v that normally starts at the origin. We're going to move it right 1 because of the -1 inside the absolute value bars. And then we're going to move it up 5 because of the +5 in the back. So from the origin, I go right 1, up 5, and then I put a dot. So that's the new point of my v for my absolute value graph. And then the -1/3 becomes the slope. So I want to go from that new blue point on the graph, I want to go down 1 and then right 3. And then to get the other side of the v, I'll go down 1 and then left 3. Down 1, left 3. And then just connect your dots to draw your new v. Ooh, that last one's really off. So kind of like that. Ooh, I don't know why I can't draw that better. Decent enough. So it's supposed to be a v. Mine looks a little funky. On 12, we want to write an example of a transform function that has been vertically compressed. So we can do 2 different notations. We could just do any fraction in the front, and then with that's the vertical compression. And then with the horizontal translation to the right, that would be inside the absolute value bars. But if you're going right, you actually want to have a minus in there. So this notation would be fine, or somebody could have done it like this. G of x equals 1/2 f of x minus 3. That would also be acceptable. For part B, if we want to do a vertical stretch, we need a number larger than 1 in front. And just a reminder, if I didn't say it before, the vertical compression could be any number in the front as long as it's in between 0 and 1 for the vertical compression in part A. Back on part B, the vertical translation down means it's outside of the absolute value bars. So it could be, down 9 like that. And let me change the colors so we don't get confused here. So kind of like that. And then remember the other option, you could have done g of x equals 4 times f of x minus 9. Either one of those notations would have been fine. And then on 13, we're just jotting down all of our key features on this graph. So before I even get far on this, I'm going to label my graph with some extra information. Negative infinity is always on the far left, negative infinity is always on the bottom. positive infinity on the far right, positive infinity on the top. And then I like to draw in my axis of symmetry and actually put the x value of your axis of symmetry. So x equals 1 is my axis of symmetry. And while I'm at it, I might as well write that down. X equals 1. That's the vertical line that goes through your vertex. So as far as domain goes, domain is all your x values that your graph covers. It's all your input values. So unless we're talking about a word problem, your domain will always be negative infinity to infinity. Again, unless it's in the context of a word problem, because this graph keeps getting wider and wider and wider as it goes down forever and ever and ever. Range is your y values. And remember, domain and range, it's easy to remember because it goes in alphabetical order. X comes before Y in the alphabet, D comes before R in the alphabet. So it helps you remember which one's which. So for range, we want all the Y values from little to big, bottom to top. So way down here, we're at negative infinity, and then we go up, 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 up to our highest Y value, which is 2. So negative infinity, comma 2 with a square bracket after the 2 because we want to include that in our answer. Is the vertex a minimum or maximum? It's a maximum because it's the highest point on the graph. The vertex itself is 1, 2, right up here, 1, 2. And then it's concave down, obviously, because it's pointing down. Zeros are x-intercepts. So zeros, solutions, roots, x-intercepts, it's all essentially the same thing. So we have an x-intercept right here at negative 1, 0. And then we have another one right here at 3, 0. And then your y-intercept is where you hit the y-axis. So that happens right about here. We'll just kind of eyeball that, say that's about 1.5. So 0, 1.5. We always want to write our intercepts as ordered pairs. And then I skipped interval of increase and decrease just because it's kind of tricky. I like to save it for the end. So interval of increase is the x values where the graph is going up when you look at it from left to right. So from left to right, we're going up over here on the left side. That's where we're increasing. So that's from an x value of negative infinity to an x value of positive 1. So negative infinity, 1 is where we're increasing. Then on the other side of the graph over here, we're going down, we're decreasing. So when x is 1 to when x is infinity, that is where we are decreasing. That's where we're going down. Because remember, you always say these intervals from little to big or left to right. And when you're talking about interval of increase and decrease, you're always talking about the x values.